Alright, so now that we have the Haasoscope Pro up and running, just want to show off some basic features and how to use this GUI. We'll look at more advanced things later, but yeah, first thing, obviously, let's put some kind of signal into the scope. So into input 0 here, there we go. So it's a BNC connection. What am I putting in? It's a 1 volt peak to peak 100 megahertz signal. You know, how do we understand this plot here? Oh, and it has some offset of 0.13 volts apparently. All right, so it's not centered at 0, as you can see. On the left, you've got voltage and divisions, right? So the first question is, how many volts per division do I have? That's over here. So at a gain of 0 decibels, we're at 160 millivolts per division. And yeah, so if we count up here, we've got 1, 2, 3, 4, 5, a little more than 6 divisions. 6 times 160, we're pretty close to 1 volt peak to peak, so that makes sense. You can change the gain, right? You make more gain, signal gets bigger. We can go all the way down to 8 millivolts per division. If you can go down to 320 millivolts per division. Yeah, 320 millivolts times 10 divisions here is about 3 volts. So not so much, but with a 10-time probe, you know, you're looking at 30 volts. Okay, so what else can we do here? We can first of all do AC coupling instead, so that's going to get rid of our DC offset and center this around 0 no matter what our signal is doing. 1 mega ohm would be for if you had a 1 mega ohm passive probe. That's not what we have right now, so we don't want to be on 1 mega ohm. 10 times probe, similarly, that would be for if you had a 10 times probe. That'll just correct this volts per division to the correct value. It's just a software thing. You can turn on anti-aliasing. Right now it's off because this channel input 0 with we're just running a single channel, so we're running at the full 3.2 gigasamples per second. So we don't need any anti-aliasing. This will be turned on later when we go down to a smaller sample rate because we're using 2 channels, as we'll see. Oversampling we'll talk about at another time. So yeah, that's about it for basically showing a channel. Oh, of course you can change the offset, so we can move that up and down. That's actually applying a voltage to the analog signal itself before it ever even gets to the ADC. So if your signal actually had a large offset, I guess I can actually try that out. So let's go to our signal generator, and on channel 1 we'll change the offset. We'll move the signal way up high, and so it would normally be like out of range of the ADC and everything, but if we apply the offset down, then we can bring that back down into the range that we can handle. So that's the idea there. Let me put that back because it's going to mess me up for later. All right, and that's it. You can't change the channel, and we only have 1 board hooked up because we only have 1 board at the moment, and we can't change the channel because we're only running in 1 channel mode. Oh, you can of course go faster and slower. So right now we're at a time base of 0 basically, so we're just showing every sample that we're taking. If we zoom in more, we get a smaller time base, so this is only 5 nanoseconds here. We can actually show the markers of each sample, which is kind of fun. So that's where each sample is, and if we go in and count, and we can pause here just by pressing the run. That'll start and stop the data taking. Then we can count, right? And we've got maybe here we've got 1, 2, 3, and a little more. So it's 3.2 samples in each nanosecond. So 3.2 gigasamples per second. So that math works out. So let's go back to running. We don't need to show the markers. And yeah, and you can go faster all the way to, I don't know, way too fast. Eventually it'll say downsample too small, but this is now sub nanoseconds, so don't really need to go much faster than that. And then you can go all the way slower too. So this is where we were before. It's a 1 megahertz signal. So from this point to here, well, I guess that's half a cycle. So that should be 500 nanoseconds, which seems to be, because this is at 600 something and this is at 1100 something, so that works out. So this is a full microsecond here. We can go slower too. When you go slower, what actually happens is you see the noise starts to kind of get smaller, and that's because we're actually averaging samples. So we can turn that on and off with this high-res button here. So that's without the averaging, that's with the averaging. So yeah, that's kind of a nice feature. You're taking so much data so fast, and you can just average these samples together in order to reduce the noise by a square root of 2 every time you do it. Okay, so that's the time base. You can change the trigger time, so where you're triggering, maybe you want to see more data after your trigger. Your trigger is here where this black dashed line is. You can also change your trigger position level here, so this is the level we're triggering on. It's an edge trigger, so we're asking that the signal go above this threshold, starting from below it. So as soon as it crosses that threshold, then we trigger. It's actually a little more complicated than that. There's this time over threshold and delta trigger quantities, which we can adjust. So time over threshold will say, I need the trigger to go over this threshold and stay over this threshold for a certain number of samples. So you can adjust that, if you want to not trigger on a really quick noise spike, but you want to trigger on just samples that stay high for a while, then you can adjust that. Delta is how far past the trigger threshold it has to go. So if it has to go 2 ADC counts or 3 or 4 above, so it's that's kind of your sensitivity. So if you don't want to trigger on things that just go a little bit above your trigger threshold and back down, then you could adjust this delta up and change your trigger that way. Okay, so put those back. Also, the exact trigger level is printed out here, which is kind of neat, in case you care. And your trigger time can go back. All right. What else here? I'm not going to mess with this PLL stuff. That's kind of an advanced feature we'll probably take out soon. readout options. Okay, we talked about high res, this whether you're doing the averaging of samples at slower time basis or not. Delay and F-delay we're not going to talk about. Those are for connecting multiple scopes. We'll talk about that later. We'll talk about the memory depth. So right now we're at, it's not 100 samples, it's 100 packets, which of course there's 40 samples in a packet, so that's actually a memory depth of 4,000 samples. You can adjust this dynamically, so now we're doing 40,000 samples, since I made that 1,000. And yeah, so you can see that we have a lot longer period of time here. Now we're recording over 12 microseconds, where before we were just recording 1.2. The downside is you can't record the data as quickly, so right now, even while we're recording it and everything, we're getting about 60 hertz drawn to the screen, which is about 0.6 megabytes per second for taking out of the scope. If you go to a higher memory depth, yeah, now it's going to slow down, so now we're at 26 hertz, but we're getting 2.6 megabytes per event now. So yeah, if you want a faster update rate, then you've got to just use a little lower memory depth, but it's pretty usable in my opinion, even at a memory depth of 40,000 samples. And that's quite a bit. I mean, you can zoom in for a while here before you really start to run out of samples. That's 40,000 points is more than most of us have on our screen still. Okay, so yeah, that's memory depth. Upsampling is kind of fun. So what that is, we'll turn on the markers again, and you can see that we have these 3.2 samples per nanosecond, right? This is, I can't zoom in there anymore. I better go down to a lower memory depth. So now we can see that we're on nanoseconds. We have these 3.2 per nanoseconds. If for some reason you really wanted to appear like you had more samples, like you kind of want to see some really fast rising edge or something, this upsampling will add more samples according to just software fits. It will interpolate and add samples along the way. So that kind of is nice. I mean, it can make the waveform appear a little bit more uniform in some cases, but it's a little slower and it takes longer to draw. Okay, other things here. We talked about the markers. You can turn the grid on and off. Some people like it, some people don't. I kind of like it. And you can turn the drawing on and off. If you turn the drawing off, it goes really fast. Now we're getting 200 hertz and 2 megabytes per second recorded. If you go to a higher memory depth, it's even. So we're getting 70 hertz and about 7 megabytes per second recorded, which is not too bad. Why do you want to do that? Maybe you don't want to draw to the screen. Maybe you just want to record the data to a file, and you don't actually want to draw it. We're going to talk about that ability to do that in another video. So that's up here in record to file. Yeah, so doing good here. What else do we need to talk about? Basic ways to start and stop runs. So you've got your usual run and paused buttons here. You can also do single shot capture, so we're just like waiting for a trigger, and then when you press run, you just collect one more event. So that's like single capture mode, and it's waiting for a trigger. Auto is means that even if your trigger threshold is low, you're still recording some data just to kind of see what's going on in the scope and with the signal. So it just records an even 5 hertz of data, and even if there's no trigger. You can turn that off, and then you're in what's called normal mode. In normal mode, it'll sit there forever until it actually gets a trigger. So when you get a trigger, then it will trigger, and when you don't, it's just sitting there. Okay, let's see what else here. I guess we can move on to showing off the FFT, since things are going well here. So FFT, we've got an FFT window that will pop up, and what you're seeing now is the frequency on the x-axis, of course, versus the amplitude. So this signal has a lot of frequencies in it. If we go slower, the time scale will adjust here, and now we're looking at larger frequencies. So since this is a square wave at 1 megahertz, you see the peak frequency here is indeed at 1 megahertz, and you have harmonics at every odd frequency. So you have 3 megahertz, 5 megahertz, all the way up to and yeah, so that's showing you an FFT of your signal there. What else? Get rid of the FFT. If we want to use the other channel, how about that? So use the other channel, we just click this 2-channel button, and now we've got a red light and we have a green light, and so the red is still the red channel that we were showing before, but now we have the green trace as well, and you can see there are 2 different colors, sort of. This really looks much more red in real life. This one kind of looks much more green in real life too. So on input 1, we can go to input 1, and yeah, it looks like it's not triggering, right? That's because over here we were triggering on channel 0. So channel 0 is the one on the left, the red one. So if you want to trigger on channel 1, we got to trigger on channel 1 just by telling it that. So you can only trigger on one of the 2 channels. Great, so now we've got both of those, and if we look at the sample rate, though, it has been halved. So if we draw our markers again and we zoom way in, we can pause. So you see we've only got, in 1 nanosecond here, we only have 1.6 samples, whereas before we had 3.2 samples in a nanosecond. So we did have our sampling rate. Because of that lower sample rate, you can see that on channel 0 and on channel 1, it's automatically turned on this 800 megahertz anti-alias filter that will make sure that no frequencies above that 800 megahertz will, well, the frequencies will get in, but the frequencies above 800 megahertz are strongly diminished, and so won't cause aliasing problems because of this lower sample rate. So yeah, so you should really think of this in 2-channel mode. It's really a like a 800 megahertz 1.6 gigasample per second 2-channel oscilloscope, which is still not too shabby. Okay, so that is 2 channels. What else here? A couple other small things. So we do have an external trigger on the back. The external trigger, I can show you by turning this around again. Okay, so we've got the external trigger is over here on the left. You can see it says 2.5 volts, 50 ohms. So that's the external trigger in. We can turn that on, and we won't be triggering, right? If I put it in normal mode, we're getting no triggers because there's nothing connected. So I would have to connect up a cable to that. So if I put in a trigger signal without messing up my camera too much. Then we're gonna start triggering again. That is set right now to 2.5 volts peak to peak, and it's going with an offset of 1.25 volts. So it's going from 0 to 2.5 volts for the trigger signal, and that works well. If we turn it down to 2 volts, it stops. So you really have to get it up to about 2.5 volts, and it'll be fine. And you could put in anything up to like 5 volts there. It's not gonna really cause it any problems. I wouldn't go too much higher than that, but what are you gonna have that's more than 5 volts, really? Okay, you also have one more thing on the back here you can see, which is this trigger or aux out, and what comes out of there is controlled by this control here. So by default it just ground, it's not being used, but you can also output the trigger signal. You can output a square wave, or you can output the ADC's 80 megahertz clock if you want to. So just kind of a nice auxiliary output. Good, so what else? I think that's doing pretty well. Yeah, I guess just to mention, you can, if you want to adjust the properties of this green channel 1 here, you can't go to more boards yet because we still only have one board connected, but we now have that second channel. When you click up on the channel, it goes from red to green, so that tells you you're adjusting the green one. You actually can just click on the traces, which is kind of cool. That took me an afternoon to figure out. But yeah, you can click on the trace. That will change what channel you're adjusting, and then you can change the offset of that channel. And you can change the gain of that channel. You can do the AC/DC coupling. You can do the 1 mega ohm. Turn the anti-alias on and off. Yeah, there you go. When you do FFT, it's going to show you the FFT in the appropriate color of the channel you're on. So if you're on channel 1, then it does that. If you're on channel 0, then it will do channel 0, which is just noise now because we have nothing plugged into it. And yeah, so that's the basic functionality. I guess one other thing I'll mention is if we look at channel 1 again, and maybe we'll go back to triggering on it instead of the external trigger so that it's not jumping around so much. you can see we're actually measuring the some things here. We're measuring the mean of the signal, the RMS, and also the rise time of that green signal. Yeah, the rise time is about 8 nanoseconds. We can kind of verify that by eye here. So yeah, coming from here to there, yeah, it's about the 10 to 90% is about 8 nanoseconds. You see when we zoomed in here, it kind of goes wacky and it doesn't know what's going on and is failing. That's because of this fit fraction thing. So this fit fraction is telling the program what fraction of the visible area to use to actually do the fit, and right now it's set to 20%, so it's only using 20% of the area that's visible centered around the trigger point to do that fit, because sometimes you have you might have multiple signals going up and down, so what do you fit for rise time? If you use the whole area, then it's gonna confuse it. But if you just have this 20%, you still get a good fit for the rise time. So that's what that's doing. But if you did have it, all the way zoomed in, and the fit was failing, then yeah, you could up this to 80%, and now it's going to be able to do the fit again for the rise time. The mean and the RMS are just the mean and the RMS of the whole signal. So if you were to move that up and down, the mean is going to go up, RMS is going to stay the same as the RMS, not relative to 0, but relative to its mean, so it doesn't change when you change the offset. Yeah, so now I think that's just about everything for the basic functionality. So yeah, of course, let me know if you have any questions. Drop me an email or whatever, and yeah, enjoy.